Hey, how's it going, guys? I'm going to go through question number 2 from the free response from chapter 6 because it is a doozy and I want to make sure that we're solid on it. All right, so I'm going to go kind of fast through some of the portions that I think are a little easier so that we can really focus on parts B, C, and D. So part A is really self-explanatory. It's just simply a free body diagram. One thing I do want to point out here is never split your free body diagrams into components if they're an answer, all right? They should always just be exactly as the forces appear in the original diagram. If you want to split them into components later, then do that, but just make a separate diagram for that, all right? So 4 points right off the bat for part A. So if you do that, 4 out of 15 already, that's awesome. Let's move on to where things get a little more dicey, like part B, all right? So part B says, write but do not solve a differential equation that could be used to determine the speed of a box as a function of time. So here's what I want us to think about, and I tried to set this up into steps for us, all right? So what we want to do is we want to identify first what are our constants and variables within this problem, all right? So when you write your equation for forces acting in the x direction, it ends up looking like this, where you've got the summation of the forces, so we got force applied plus the negative drag force is equal to the mass times the acceleration in the x. And looking at this, we can tell, all right, my constants are going to be force applied, k, and mass, and then my variables are going to be simply velocity and acceleration. All right. Now, if we refer back to our problem says we want to know a differential equation that can be used to determine the speed v. So that's the thing that needs to jump out of us. We want an equation for speed v. When we hear differential equation, we want to identify the function that we care about. The function that we care about, according to the problem, is v. We want to know a function for velocity. From there, we want to identify potential derivatives of that main function within our equation. So if we look at that, well, we know that acceleration is the first derivative of velocity. So we can rewrite acceleration as dv dt, which is the derivative of velocity with respect to time. So then what we can do is we can rewrite our original equation with derivatives of that main function, okay? So what that ends up looking like is FA minus KV, where V is our main function, is equal to the mass times dv dt, which represents our acceleration, except we've rewritten it as the first derivative of velocity. And so now this represents our differential equation because we have our main function and then a derivative of that function. And that gets us through part B. Now, part C says determine the magnitude of the terminal velocity of the box. All right, so the terminal velocity of the box. Here's what we need to recognize there. We have to recognize that the terminal velocity is where the acceleration is equal to 0. All right? What this means is that acceleration is equal to 0, so dv dt is equal to 0. So we have to evaluate that equation that we just wrote from B at dv dt equals to 0. So that's just a simple substitution. We take our original equation, we substitute 0 for dv dt, and then we solve our equation, and we get that our terminal velocity is going to be equal to FA divided by K. All right? Once we had our function, we could just plug that in. Part C, the really fun part. Part D. Use the differential equation from part B to derive the equation for the speed of the box as a function of time. Okay, let's go back to our list here, and let's kind of pick up where we left off. So we left off after we had rewritten our differential equation to get our main function v and the derivative of function v within it. The first thing that we need to do in part D is we want to rearrange this equation to get all of our v's with dv and all of our t's with dt. Now, if you look in this equation, there are no t's, so that's not a big deal, and there's only one v. The rest of these, remember, are constants. Think of these as just being numbers. I know it looks confusing because of the notation, but FA, K, and M are simply constants. So I want to get this whole thing rearranged so that V and dV are hanging out, and then dt is on the other side of the equation. dV and dt need to be on opposite sides, okay? This is also valid for any variables. Like, let's say instead of dV dt, we had dx dy or dy dx. We would go the same approach. We'd get all of our x's on one side with dx and all of our y's on one side with dy. It does not matter where our constants end up, okay? I don't care where they end up. I'm going to keep them all together just for simplicity's sake, but it doesn't really matter where they go. So what we end up getting if we move all of this stuff around is I put dt on one side, and then I put everything else with dv on the other side. The thing that I really care about here is that this v is with this dv. That's the biggest thing I care about. The constants, again, are just along for the ride, and there were no other t's in the equation, so dt just gets to hang out all by its lonesome. This right here is getting you a point just for rearranging and getting your v's with your dv. If you haven't done integrals yet, if you haven't done calculus yet, just remember here, you want to get relevant variables with each other. V's with dv, t's with dt, all right? Now, the next step. We want to integrate both sides in order to undo dt and dv. Because if we look back at what our question is asking, part D is asking for an equation for the speed of the box as a function of time. So we want to end up with v as a function of time. Currently, we've got this dt and dv here. We don't want that. Now, the way that we can undo dt and dv, which are derivatives, is to take the antiderivative. Antiderivative also referred to as an integral. So we simply just state that we're integrating both sides. This earns you another point, recognizing that you need to integrate both sides. All right? So we haven't really even done any calculus yet. We're just simply setting up this problem. The next step is to plug in our bounds. And this is just a hard step, I think. All right? This is where we really need to pay attention to a statement within the problem that says, assume that v equals 0 at time equals 0. So when we're talking about bounds, this represents like the area over which you are evaluating the integral, all right? And when it says in the problem, assume that the velocity is 0 at time 0, think of that as your initial bound. So these generally are going to have an initial bound of 0 unless they say otherwise. To get a general expression, which is what we want here, we want velocity as a function of time, the upper bound is going to be the variable that you are evaluating. So what I mean by this is your initial bound goes here. They told us within the problem that it's 0. Your upper bound is whatever you're evaluating. So this is going to go from 0 to t because we're looking for a general expression of t. Here, this goes from 0 to v because we're looking for a general expression of v. All right. The next step is to evaluate. All right. Now, this is the really calc-heavy part, is to evaluate it. All right. Now, if you don't know how to do this, because you will know how to do it by May. And even if you just attempt the integral, okay? Just attempt to do this integral right here, you get 4 out of 5 points, okay? So if you were able to get to this point right here, you're at a 4 out of 5, which is a very high 5 on the exam, all right? This next part, if you don't know how to do it, no big deal. People who have done integrals before, watch and see if you can figure this one out. So there's our integral. The integration on the left side is really easy. It's just dt, so that we get t from 0 to t. Over here, I'm going to take the m out just to make it look a little bit cleaner, because m is a constant, and it's, again, just along for the ride. And so then I get this expression right here. Remember, m, fa, and k are constants. I'm just going to keep reminding you of that. Now, on your equation sheet is this statement right here. The integral of dx over x plus a is equal to the natural log of x plus a. That's fine, but it's really specific. A more general expression for this is the integral of dx over a plus bx. This is equal to 1 over b times the natural log of a plus bx. This is not on your equation sheet. You should just remember this, okay? The key difference between these is that there's this 1 over whatever constant is attached to your variable here. So that 1 over b is hanging out front. That's going to be important for when we take the integral here. So when we take the integral here, what you see is that this m is still hanging out here because it's a constant. I now have this negative 1 over k out front. The reason I have this negative 1 over k is that k is that b value here. All right, so if you look in here, there's a negative k attached to our v. That's like the plus b that's attached in here. So we got negative 1 over k times the natural log of f sub a minus kv. And we're evaluating that from 0 to v. So it's pretty much a one-step integral there if you remember this rule. All right, now we need to evaluate our bounds. So when we evaluate our bounds, think of it like a final minus initial. All right, so we're going to plug in the final and then we're going to subtract the initial. So for t, that's real easy. We get t minus 0. And then this is equal to negative m over k. I just factored out the negative 1 over k times the natural log of f sub a minus kv, because I plugged in the v, minus the natural log of f sub a, because I plugged in the 0. So when I plug in 0, that expression goes away, and we're just left with natural log of f over a. Subtraction of two natural logs is the division of 1. So I'm going to rewrite this as t is equal to negative m over k, which is negative m over k times the natural log of f sub a minus kv over f sub a. Now, remember what we're looking for here. It's easy to kind of forget what you're looking for. We are looking for the speed as a function of time. Currently, speed is inside of this natural log. I need to get it out of that natural log. Okay? So I'm going to put everything, I'm just going to use e. I forget what the exact word is, but I'm going to use e. All right? So I'm going to take each side to e. And what I end up getting is on this left side, and I also brought k over m over here just so it makes it easier to isolate this. So we get e to the negative kt over m is equal to f sub a minus kv over f sub a. We are able to undo the natural log by using e here. Then if I'm just solving for v, it's just algebra at this point. So I multiply by f sub a, so I get f sub a times e to the negative kt over m is equal to this. And then a few more steps, and I can get that v is equal to f sub a over k times 1 minus e to the negative kt over m. Now, if you want to know if this is correct, we were given initial values. Assume that v equals 0 at time equals 0. So we could plug those in and see if we get v equals 0. So if I plugged t equals 0 into this would be negative k times 0 over m. So this would be e to the 0. Now anything to the 0 is 1. So we get 1 minus 1 within these parentheses. And 1 minus 1 is 0. So 0 times this is 0. So v equals 0 at time equals 0. We are set to go. Final part is part E. All right. Sketch a graph of the speed of the box as a function of time. And it says explicitly label any intercepts, asymptotes, max or min with numerical values or algebraic expressions. So this is velocity versus time for the terminal velocity. So we see that at the beginning of our motion, we have a velocity that is increasing, and it's still increasing, but it's increasing at a slower rate. And eventually, it's going to approach this horizontal asymptote here. That horizontal asymptote is at FA over K. I get this from part C, if you recall. And in part C, where's my sheet here? In part C, we determined that the terminal velocity is equal to F sub A over K. So this horizontal asymptote here represents my terminal velocity. All right, guys, I know that was a lot. Hopefully this helps clear things up a little bit. In general, problems like this, you can work through using these steps here, okay? So try and rework through it yourself. See if you can at least get to this point right here. If you can get to this point, then that's a really good place to be, all right? Don't worry too much about actually evaluating the integral right now. That will come. All right, let me know if there's any more questions. See ya.